Jai Hind to all. My name is Dr. Divya Sharma. I am Assistant Professor in Ajay Kumar Garg Engineering College. My today's video lecture is on non-linear applications of IC op-amps. This topic is taken from Integrated Circuit. Its code is KEC 501. Now, first non-linear application of IC op-amp, that is basic log anti-log amplifier using diode and BJT. So both these applications using diode and BJT that require compression of analog input signal, linearization of transducer that have exponential outputs and analog multiplication and division. So these are the these two applications are used because of this compression of analog input signal. Now basically when we will start with this basic log amplifier using diode and BJT, first you should know use of diode in logarithmic amplifier, because there is a use of diode in logarithmic amplifier. So diode is, as you all know, this is the symbol of diode, in which you have this one is positive terminal and this one is negative terminal. Its VI characteristics are, here this is forward biasing and here this is reverse biasing. So this is the voltage current characteristic of diode. Now we have to use this diode in when we are designing a circuit for logarithmic amplifier using first diode. And now this is the IV characteristic of a diode. I is equal to I0 e की power Vf upon eta Vt minus 1. So I is the current here. We have to find out current. Now I0 is reverse saturation current. I की power EVF. VF is your forward voltage across diode. Eta we are using here 2 for silicon and 1 for germanium. So Vt is voltage equivalent of temperature at room temperature, that is 300 Kelvin, or you can consider 26 millivolt for this. Now minus 1. So we have to calculate this equation. I is based on these parameters. Now IF is equal to what? Because we are using here forward biasing. Now this is the circuit diagram, basic logarithmic amplifier using diode. This is operational amplifier. Diode is connected in the feedback of this operational amplifier. Here our resistance is connected, input voltage is connected at the inverting terminal. Now I current is across R resistance and IF current is across VF. VF is the forward voltage developed across this diode. So current flowing across the diode is represented as IF, and here we have to find out output voltage. So first you should know IF is equal to I0 e की power Vf upon eta Vt minus 1. So this is the current equation of diode. Now IF represent forward current and Vf represent forward voltage. Now here in this equation we are assuming this e की power Vf upon eta Vt is greater than 1. If it is greater than 1, then it means IF is equal to I0 in bracket e की power Vf upon Vf upon eta Vt. If we are assuming this one is greater than 1. So here IF is equal to I0 e की power Vf upon eta Vt. Now take log here on both sides, taking log on both side, or you can say natural log, take natural log on both side, and here ln IF is equal to ln I0 plus ln e की power Vf upon eta Vt. Right? Now here you will get ln IF is equal to ln I0 plus ln, here this is ln means in form of log, and this is e की power Vf upon eta Vt. So log exponential is cancel out and we will get here Vf upon eta Vt. Now from this equation we have to find out Vf, because we have a requirement of Vf when we are using diode in the feedback of log amplifier using diode, right? So Vf we have to find out. So Vf is equal to first ln IF minus ln I0 is equal to Vf upon eta Vt, right? Now Vf is equal to what? Vf is equal to eta Vt ln IF minus ln I0, right? So this is the equation where we are getting this Vf is equal to eta Vt ln If minus ln I0 by using this diode current equation. So we have a requirement of this equation when we are solving the log amplifier using diode. So this is the circuit diagram of log amplifier using diode, because diode is connected in the feedback and we have to find out the output voltage for this circuit diagram. Now how we can find out output voltage for this circuit diagram? Here you can see, here is IB is equal to 0 due to short virtual ground here. So I is equal to IF. If IB is equal to 0, it means I is equal to IB plus IF, and IB is equal to 0 because due to high input impedance. So I is equal to IF here, right? So I is equal to IF, and IF is equal to what? Means I, if you are calculating I here, I is equal to V in upon R, and I is equal to IF. So IF is equal to what? IF is equal to V in upon R. Okay, now I is equal to IF is equal to V in upon R. And from the previous slide, for the equation, current equation for diode, that is equal to Vf is equal to eta Vt ln If minus ln I0. Why we are solving this equation, this circuit diagram? Because we, in this basic log amplifier using diode, log amplifier gives an output which is proportional to the logarithmic of the applied input voltage. It means what? There is a relation in between output voltage and input voltage. So output voltage V out is equal to ln, it should be directly proportional to ln V in. So we have to find out input voltage, then we can find out the relation in between output voltage and input voltage. So for this circuit diagram, we have to find out input voltage for this output voltage. V output, we have to find out V output in form of V in. Now I is equal to IF, and that is equal to V in upon VR. So let us consider this is equation 2, and from this circuit diagram, V out is equal to minus Vf. V out is equal to minus Vf, and Vf is this equation eta Vt ln If minus ln I0. So put this equation Vf in this equation, V out is equal to minus. So put this value Vf here, and you will get here equation V out is equal to minus Vf. Put here minus Vf means minus eta Vt ln If minus ln I0. And If, you know, this is If is equal to what? If is equal to V in upon R. So V out is equal to minus eta Vt ln V input upon R minus ln I0. So V output in this form, V in upon R and I naught. Now can you put this V in upon R? So you can take like this, V out is equal to minus eta Vt ln, can you write down it like this, like log A minus log B, it means log A upon B. So ln V in upon R upon I naught. So I naught is here fixed DC voltage. So you can write down it I naught R is equal to I naught R is equal to V reference. So final equation is in form V out is equal to minus eta Vt ln V in upon V reference. It means what? It means V naught is directly proportional to ln V in. So this is the proof. We have to do it in this basic logarithmic amplifier using diode. Now limitations in log amplifier. So what are the limitations of this log amplifier using diode? Here Vt is equal to T upon 11600. Now here if there is a change in the value of temperature, it means there is a change in the value of Vt. And if there is a change in value of Vt, then it means there is a change in the output voltage, because output voltage here, output voltage depend on this Vt. And second limitation is that, second limitation, V output is depend on eta. Now output voltage depend on ideality factor, that is eta. It may be 0, it may be 1, or it means what? Its effect on the circuit diagram as that dynamic range of this amplifier will reduce. So these are the limitations in this log amplifier using diode. Now second, we will start with this log amplifier using transistor. So here, what is the difference in between log amplifier using diode and log amplifier using transistor? In that log amplifier using diode, we are connecting their diode in the feedback of the circuit diagram. Now here, in basic log amplifier using transistor, we have to connect transistor in the feedback of the circuit diagram. Now let us consider, this is a circuit diagram, this is operational amplifier, this is your transistor which is connected in the feedback of this operational amplifier. Here R1 is connected and here input voltage is connected at the inverting terminal. Okay. Now what is first, what is the difference in between these two? Here in that log amplifier using diode, we are connecting their diode in the feedback. Now here we are connecting transistor in the feedback. Now base is grounded, collector is now here you can see this is a transistor, this is base of this transistor NPN. Now this is collector, this is base, this is emitter. If it is grounded, now here this is also virtually short. Virtually short means it is also grounded. You can assume that IC is connected to ground. If it is also connected to ground, base is also connected to ground. If you are taking this IC, means collector and base are short circuit, then you can say it is also works as, means this EB, it works as a diode. So then you, if it is like it acts as a diode, then it means output voltage is directly proportional to input voltage. But here we are considering transistor, and the current equation for this transistor is equal to what? As you all know, IE is equal to IB plus IC. If this IE is nearly equal to IC, sorry, IB is less than IC, IB is less than IC, so we can say IE is nearly equal to IC. And IC is equal to what? IC means for this transistor, current equation is equal to IC is equal to saturation current e की power VB upon Veta minus 1. Now from this equation, we are assuming that e की power VBE upon VT is greater than 1. So we can say IC is equal to IS, IC is equal to IS e की power VB upon VT. Now and IC is equal to IE equal to saturation current e की power VBE upon VT. Now here from this circuit diagram, I1 is equal to what? I1 is equal to V in upon R1. So IC, and that is equal to IC because IB is here 0. So I1 is equal to IC is equal to V in upon R. This is, or you can, this is R1 is R. Okay. Now here you know the current equation means IC is equal to V in upon R1 and IC is equal to IS e की power VBE upon VT. Now can you equate this equation 1 and 2 equal, means equalize this equation 1 and 2, that is equal to what? V in upon R1 is equal to IS in bracket VBE upon, sorry, e की power VB upon VT. Now from this equation we have to find out the value of VBE. So if we are equating this, VB is equal to what? VB is equal to minus VT ln V in upon ISR, and in this equation VBE, VT and IS are the temperature dependent variable, and from this circuit diagram V out is equal to what? V out is equal to minus VBE, and VB is calculated here, that is equal to what? Minus VT ln V in upon ISR. Now put this equation VBE in V out is equal to minus VBE. So put this equation value of VBE in this equation V out. So V out is equal to minus VT ln V in upon V reference. Now this output voltage is also in the form of input voltage and V reference voltage. Here V reference is what? V reference is here VBE, in VB equation ISR is considered as V reference. So this is the final equation. V output voltage is equal to minus VT ln V in upon V reference. Now this in this equation also V out is also proportional to I in, ln I V in. So V output is directly proportional to ln V in, means logarithmic input voltage V output is equal to, right? Now here in basic log amplifier using transistor and the basic log amplifier using diode, have two limitations. First one is that there is a change in the temperature, then Vt is also changed, and then output voltage is also changed, and the second one is it depend on the eta. Now here using this basic log amplifier using transistor, it removes it overcome the limitation of first limitation of logarithmic amplifier using diode, that is it is not direct, it is not means eta is not present here in this final equation. It means it is output voltage is not depend on the eta value, right? Now the third one is temperature compensated log amplifier using diode. So why you are using this temperature compensated log amplifier using diode? In this we will try to overcome the second limitation also, which is dependent on the temperature, means output voltage is dependent on the temperature. So here in this we will try to overcome that problem, that limitation of logarithmic amplifier using diode and using transistor. Now this is the circuit diagram of temperature compensated log amplifier using diode. Here this is the basic log amplifier, already we have done using diode. Now here input voltage is connected in the inverting terminal, here resistance R. Now diode D1 is connected in the feedback of this A1 operational amplifier. Now after this we are connecting here compensating network, in which here is the second diode D2 is representing here, and D2 is same as D1, means properties of D2 means diode 2 is same as D1 diode. Now here this is the operational amplifier 2 and I reference is connected at the non-inverting terminal. So I reference here IB is equal to 0 due to virtual ground. So I reference current is also flowing through across this diode D2. So I reference is current across this diode D2. Now here and RF resistance, means feedback resistance is connected at the connected in the operational amplifier A2, R1 resistance connect and RT. RT is represented as temperature dependent resistance. So temperature compensated logarithmic amplifier using diode is a combination of basic logarithmic amplifier plus compensated network, and already we have done this basic logarithmic amplifier and find out the output voltage for this basic logarithmic amplifier. Now here we have to find out output voltage, in which we have basic logarithmic amplifier and compensated network. So we have to find out V naught. Now it overcomes the disadvantages of log amplifier using diode and transistor, and D2 has matched characteristic with diode D1, and IT temperature dependent resistance. If temperature increases with increase in the temperature, it means positive temperature coefficient of the resistance. Now here D1, D2 diodes are matched in all respect. It means VT and saturation current, that this is I naught is represented as reverse saturation current. So it means VT and I naught both same, and change in them with the temperature is also identical. So next point is that you should remember, due to infinite impedance of A2, IB is equal to 0. Naturally current through D2 is equal to I reference. Now I reference is used for developing a constant reference voltage. Now we have to find out, these are the points we have to remember when we are doing this temperature compensated logarithmic amplifier using diode. Now here we have to find out, now we have to find out the output voltage of this circuit diagram. So here first we should know this V1. V1 is the output voltage of the basic logarithmic amplifier, that is equal to what already we have done in the previous slide. V1 is equal to minus eta Vt ln V in upon R resistance minus ln I naught. Now this is VF2. VF2 is the forward means voltage, VF2 voltage across this diode D2. Now V naught for this whole circuit diagram, V naught is equal to what? V naught is equal to V1 plus Vf2, and V1 is the output voltage of logarithmic amplifier using diode, and Vf2 is, you have to find out Vf2 by using current equation of diode, forward current equation of diode, right? So first V1 already we know, V1 is equal to minus eta Vt ln V in upon R minus ln I naught, and Vf2 is equal to eta Vt ln I reference minus ln I naught, right? Now here V2 is equal to what? V2 is equal to V1 plus Vf2. So put this value V1 in this equation V2. So V1 and Vf2, put all these two equations in the value of V1 and Vf2, and we will get here V2 is equal to what? V2 is equal to minus eta Vt ln V in upon V reference. Put this equation in this equation, V2 is equal to V1 plus Vf2. V1 is equal to minus eta Vt ln V in upon R minus ln I0 plus eta Vt ln I reference minus ln I naught. So by using this equation, this one is cancel out by this one, and we will get here minus eta Vt ln V in upon R plus ln I reference, okay, and minus eta Vt, here is minus, so ln is equal to minus eta Vt ln V in upon I reference R, and this is equal to what? This is equal to V reference. Now V2 is equal to minus eta Vt ln V in upon V reference. So this is the value of V2. Now here V out is equal to what? V out is equal to, sorry, that one is V2. V2 is equal to V1 plus Vf2. Now find out V out. V out is equal to AVF2 into V2. This is the average gain of Vf2, means this second amplifier, that is equal to what? AVF2 is equal to 1 plus Rf upon R1 plus RT. Rf upon R1 plus RT. AVF, it's this value is AVF, and V2 is already find out that V2 is equal to minus eta Vt ln V in upon V reference. So put this value Vta here in this equation V naught, and AVF, put here this value AVF, and you will get here V naught is equal to 1 plus Rf upon R1 plus R2 RT into minus eta Vt ln V in upon V reference. Now by putting these values, we will get here V out is equal to K is your constant, ln V in upon V reference. It means what? It means here output voltage is not depend on the temperature parameter, that is Vt and I naught. So this, when we are not getting temperature dependent parameter in the output voltage, it means what? It is overcoming the limitations of logarithmic amplifier using and diode and transistor. Now these are the applications of logarithmic amplifier to perform mathematical operations like multiplication, division. Second one is power extraction, and the third one is square root calculation. So these are the references of this topic, that is first one is Gaikwad operational amplifier and linear integrated circuits, 4th edition, Prentice Hall of India 2002, and the second one is Franco analog circuit design, this is discrete and integrated TMH, 1st edition. Thank you.